So firstly, let's see, I want to go ahead and open up an example of lab notebooks. I started grading the first section of them for your section 304, and I wanted to touch on the lab notebook example and show everybody here that is in the Canvas section. If you go into files, there should be a lab notebook example, and I wanted to review it with everybody here so that way that everyone can make sure that we don't lose any points for miscellaneous small things. So right here, so as this is an example, make sure to, whenever you submit your document, go ahead and have your name here, chemistry 2141, and then your section right here next to it. And then you can either put the title right here in the header or at the top or at somewhere, you know, in the section to have some sort of statement towards what we are going to be performing as the experiment for the week. And then also go ahead and put the date here, just as a formality, as if you were turning this in person. So the purpose, everyone's doing well on their purpose so far. It's looked good. Everyone's understanding the idea of why we're performing the experiments. The main thing I've noticed is that people are still getting the apparatus and instruments confused. So from the first week, we had a quiz that was asking the difference. Make sure that you understand here the difference between an apparatus and instrument. So the instrument would be a machine that we'd be using. For instance, in the first week, we had a melting point machine. So that would be an example of a machine. However, for apparatus, that would be something like a round bottom flask or Erlenmeyer flask or graduated cylinder. So just make sure that you understand the main difference between those two and then put them into the separate sections, because I've noticed some people are putting either everything in the apparatus section or everything in the instrument section. Additionally, in the apparatus section, make sure that you don't just place their generic statement. For instance, I've seen a few people in the first lab, they had placed vacuum filtration, and that is an action that you perform, and it is not like a singular object. The vacuum filtration apparatus would consist of the vacuum filtration flask, a rubber stopper in order to secure your ceramic filtration vessel, and just make sure to list out every individual component, not just, you know, vacuum filtration apparatus, because that's too generic. We need to know the tools that you would be using walking into a lab. And if you wanted to re-perform this experiment, just utilizing your lab notebook, you'd need to be able to walk in and say, okay, I need A, B, and C items in order to perform this, and A, B, and C apparatus in order to perform this experiment. And then I need this instrument in order to analyze the experiment that we perform with the given apparatus. Let me take a look real here. Okay, yeah, I saw your message, Taylor. All right, and then so next, everyone's doing great on the hazards. Make sure to just go ahead and, if you're not creating them like this, I would prefer that everyone go ahead and perform this sort of table within it. If you're either writing it or putting it into Word, try and format it slightly like this. The main idea is that firstly, we want to make sure all the chemicals we're utilizing within the lab, we understand that even though we're only performing this online, we need to understand that if we were going to be walking into a lab, what safety precautions we need to perform in case we spilled it, or in case it became as here, skin contact, eye contact, inhalation, or ingested, what we should do upon those things. So this is the safety precautions we need to understand for experiments. Additionally, the waste needs to be understood as well, where we would place it, because we'll have separate carboys where you'd place it, and you don't want to mix organic waste into aqueous waste, because those two are separate, and then it'll create two phases. And whenever the waste department comes, they can, you know, find the facility for improper disposal. So make sure that we understand what type of waste it is. And then pre-lab calculations, any sort of equations or calculations, even just theoretical yield, percent recovery, go ahead and you can just put the equation there. If there's no pre-lab calculations, just put like a small equation there, and then you're good to go. Procedure, everyone's doing great on that so far. You just need to make sure, you know, you just rewrite it in your own words on how you would perform the experiment. Y'all are doing great to that. Changes in procedure, y'all are doing fine on there as well. There hasn't been any major changes we need to worry about. The data, finally, utilize the data that we're given on Canvas, and then you'll go ahead and place it into that section. And then post-lab calculations, everyone's doing fine there. Conclusion, y'all are doing great there. And then post-lab questions, just make sure if you don't place the question into it, that you write in a full, complete sentence, so that way that it's written out, not just, number one, answer is 12. Like if somebody looked at that and then they were curious, well, what was the question? What is 12? What does that mean? 12 atoms of helium were found in a sample of this and that. That's a better description towards something rather than just throwing an answer on the page. So either write the question and then put the answer under it, or write out a full sentence that puts both the question and answer, together within there. Yeah, and so mainly just make sure that you understand the difference between apparatus and instruments. And as you can see here, it explains it. You can find this lab notebook within the Canvas portal under files. There should be lab notebook example section. And let me see if I have any other notes for this. One critical answer that I noticed most people forgot to mention was if you put a hot solution into an ice water bath. This is a good measure for anything in regards to chemistry or even real life example. Never put hot glass into cold water or into cold really fast, because it can shatter. So if you placed a hot solution into an ice cold bath, not only would it mess up the sample in terms of the recrystallization method, it would also potentially shatter the glass and then spill your entire solution into the ice water, and then you'd basically ruin the experiment and possibly just entirely ruin your experiment. So you really want to make sure to never place something that's scalding hot into some ice cold freezing situation. And that's a safety feature that everyone needs to know, not only for lab, but also for real life examples, that you should never put, a hot piece of glassware into ice cold water. And I believe that's about it for the lab notebook that I wanted to review today. So we're going to switch over. Next, going to discuss that we're going to go ahead and review the module as well. I wanted to just make the announcement to make sure, if you haven't watched the video from last week, to please watch that video. If you need any review of fractional distillation, it should be understood from that. And let's go ahead and open up the module here, and let me have this. One moment. Okay, so firstly, we're going to go ahead today and we're going to read through the simple distillation manual here. And I'm going to make the announcement that the fractional distillation last week's lab notebook was expected to be due by this Sunday. Additionally, the simple distillation also due this Sunday, and the quizzes due today, both of them. They were extended out for this long. Everyone should be able to access the internet and power by now. It's been almost 2 weeks. So please let me know directly by email if you're still having any issues with regards to any power or internet issues. Otherwise, we'll go forward that everyone needs to review these videos if you have not reviewed them yet. There's the 3 videos here for an example of simple distillation, and the concepts covered here are going to be much easier to comprehend if you've already reviewed the video for fractional distillation and all of the modules for fractional distillation. Thirdly, please complete your lab notebooks. Since we have such a shortage of people this week, we're not going to worry about if everyone's had their pre-lab completed, but I would assume since we're this far into the week, most everyone's already working on, if not completed, with their notebook. Go ahead and complete your quiz for this and make sure that your fractional distillation one was completed as well, in case you had any power issues last week. And then, so this is a good example I wanted to go ahead and review with everyone. And so on the left, you can see all of the parts of our experiment here that are separated out. All of the utensils or apparatus, as they would say, within your lab notebook that we'll be utilizing in order to perform the simple distillation. So these are the apparatuses, right? These are all of the pieces of glassware we're going to use in order to perform the simple distillation. However, a heating mantle or an electric hot plate would be the machine in this case in order to heat up the samples and then allow, or heat up our sample in order to allow it to perform simple distillation over into a receiving flask. So I wanted to zoom in here for everyone so that we could see if I can get that better over here. So what we do here is this round bottom flask. We always want to coat the inside of the round bottom with a little bit of grease, or on any of the joints here, you want to put a little grease around them so that way it creates a uniform fit. And so that way whenever the glass expands, it doesn't get stuck onto there and possibly crack or just get stuck and you can't remove it after you're done with your experiment. And whenever you create that closed system, it becomes a lot easier for the distillation to perform a lot better within lab. So you have your round bottom here. You would put some boiling chips into there or a stir bar in order for it to be able to boil off of the little thing that you have inside of there, whether it be boiling chip or stir bar. And as well, stir bars are really good for this, mainly because it continues to stir your solution and it keeps the heat uniform throughout your entire solution. The same kind of concept with the boiling stones for the heat to be able to disperse throughout your solution, not just get like a hot spot within the center and maybe another part of it's not as hot as it needs to be. The clips are used in order to hold together the joints. And so in case gravity takes effect and separates it while in the middle of your distillation, that'll just kind of keep it together a little better. Then we have the little apparatus here that allows the boiling of our solution to go up. And then once it comes up to the top here where the thermometer is at the still head, then it'll recondense and then cool back down, coming down through here through the condenser. And so with a condenser, what happens is we want to put a hose coming from a water source going down from the bottom up through the condenser and then coming out of the top of the condenser. And so what that does is it brings cool water up through the condenser and it meets with your hot distillate and cools down going the opposite way down the condenser. And then the hot water that has received the heat from your distillate will go out of the system. And so it will go through the condenser and then out and then come out of this adapter at the end, coming down and then falling into a graduated cylinder for the example that we have here, or some sort of just receiving flask. One big thing here is this thermometer. We can see that it's put up here. It's not down into the solution. It's actually put up here, and it's called the still head. That is where basically your simple mixture, it'll be just, in this example of the lab manual, the cyclohexane. When the cyclohexane boils up, when it comes to the still head, it'll be at cyclohexane's boiling point. So you'll read at the top of the still head on the thermometer that exact temperature whenever the cyclohexane is in the gas form. It'll be at its boiling point, and then it'll recondense up there because the heat isn't up at the top of the still head anymore. It's just the heat of the cyclohexane gas, and then it will recondense up there because there's no heating mantle, everywhere in the system. It's just only at the bottom with the condensing, or with your round bottom flask that has your solution in it. And so it condenses at the top, and then the condenser on the right-hand side here, the long sort of cylinder here, has water running through the outside of it, which allows it to take the heat out of the system, taking the heat from the cyclohexane in the gas form and cooling it down back into a liquid and allowing it to come down the condenser and come down out of the apparatus. And so after that, let's see any other last things here. The post-lab notebook, just go ahead and make sure to finish that up and then have it uploaded this weekend. And yeah, so then we'll review the data here at the end of our meeting, so that way everyone understands where to access that. So next, I will go ahead and open up our lab manual so that way we can review it together. So let's take a look. All right. So right here at the top, we can see here just a brief introduction into the experiment, and it's not too critical in terms of the main points that we need to understand for the experiment. So I'm just going to briefly jump to some of the points here that I have highlighted that'll be critical in terms of understanding the experiment. And these equations, I've already had the other sections or other people ask me, where do we utilize this? I would just have these equations placed into your lab notebook as a formality of understanding the experiment itself, rather than to have to be utilizing this, because we won't be necessarily using Dalton's law, Route's law in order to calculate much in the experiment. So I would just go ahead and have that in your lab notebook for formality of stating that that was in the lab manual. However, the main thing here, the two of the laws, Dalton's and Route's law, that you have encountered in previous courses in chemistry and or physics are critical to understanding the phenomenon of distillation. So firstly, Dalton's law, which is the total pressure of the system is the sum of all of the partial pressures. So if you have three substances within a system and it's A, B, and C, then the pressure of A plus pressure of B plus pressure of C is equal to the pressure of the total system together. Secondly, Route's law, the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So in a system, we can look here, P solution, right here, vapor pressure of the solution, which is the total vapor pressure of that solution, is equal to X of solvent with the mole fraction of the solvent. And we'll look further down to explain out what the mole fractions calculations are, as well as P solvent, the vapor pressure of the pure solvent. And that is a given vapor pressure that would be for a pure solvent, for example, water as a system, having a specific vapor pressure at a given point. It would be a number that would be a standard number given to you. So going forward, in this idea, we're going to be utilizing the concept of a closed evacuated system. And so going forward, we would see the magnitude of this vapor pressure at a given temperature is called the equilibrium vapor pressure of the liquid at that temperature. And so what we're talking about here is this idea and concept of boiling point and the statement of equilibrium vapor pressure. And the reason that we're doing that is because we need to understand going forward that vapor pressure is temperature dependent, as shown in figure 4.1. And so we'll go ahead and review this here once we get through this next portion of statements. As the temperature of the system rises, the average kinetic energy of the liquid in the molecule increases, thus facilitating their escape into the gas phase. So here in figure 4.1, this is the main concept that we're going to be covering in simple distillation that everyone needs to understand. And this idea is more relevant towards something in regards to vacuum distillation. So when we look here at this graph of the dependence of vapor pressure on temperature for a liquid, you can see here on the x-axis, we have temperature from 0 to 60 degrees for some given volatile liquid. And we have the vapor pressure and torr from 100 to 760. So 760 torr, or 1 atmosphere, is the universal average that we use in systems. So at a given temperature, a boiling point of 60 degrees Celsius for this given substance, it boils exactly at 1 atmosphere at 60 degrees Celsius. So if we were to reduce the pressure down in a system using something like vacuum distillation, or using a pump to pull vacuum, which reduces the whole system's pressure down, we would actually end up reducing the boiling point down. So you would see here at 500 it'd be somewhere in between 40 and 50, we'll call it 45 degrees Celsius or so. And then as you see, as we reduce the vapor pressure down, it actually reduces lower and lower the boiling point relative. So what happens is if you have a very strong pump onto a round bottom flask, you can actually reduce the vapor pressure down so low that it actually ends up boiling over your solution or your volatile liquid, even at room temperature. So as you see here, if you have something near, and room temperature is around 20 to 23 degrees Celsius, if you have something around 150 or lower, even here, this volatile liquid starts to boil. And you have to remember that as a concept, that we think boiling point, we think, oh, 100 degrees Celsius water. You have to remember that that boiling point is not fixed. It is temperature, it is pressure dependent in this given system because it's a closed system. So you're reducing the pressure, and you can remember PV is equal to nRT. That's the common idea. So if you reduce the pressure on the left side of the equation, simultaneously you're reducing the temperature on the right side, or the equation has to balance out. So as you reduce the overall pressure of a system, you simultaneously reduce the overall boiling point of the system. So we can effectively boil something off at room temperature if we reduce the pressure low enough. And this is just a good concept for everybody to understand with relations to boiling point and pressure. And one thing is that you will never want to heat a closed system because you can either have an implosion or explosion, depending on if you're reducing the pressure, or if you just have in a container and you heat it up too much, then your glassware could possibly explode. So in this system here, the total pressure above the liquid is defined by Dalton's law of partial pressures, given within equation 4.1 here, and it is equal to the sum of the partial pressures of the sample and of air. The partial pressure of the sample is equal to its equilibrium vapor pressure at the given temperature. And so that is related up here to the pressure and the given temperature. And as you can see here by equation 4.1, the total pressure of a given system is equal to the pressure of the sample plus the pressure of the air within that given system. And so going forward, we would understand that if the temperature of a liquid is raised, the equilibrium vapor pressure will rise as well. Vice versa, if it's reduced, it would reduce as well. So they're directly related, they're directly dependent on each other. And so if we did that, it would have a net effect of displacing some air. So at the higher temperature, the partial pressure of a sample will be larger percentage of the total pressure, because as the sample increases, then the pressure of the sample increases, then the pressure of the air decreases if you have an equilibrium system of a total amount of pressure within a given system. So going forward, we would understand that when the temperature of a liquid is such that the equilibrium vapor pressure of the sample equals the total pressure, the rate of evaporation increases dramatically and bubbles form in the liquid, which comes to this final idea that everyone understands already, but this is just the pretense of the concept of the boiling point. So as we were talking about before in discussing from our figure 4.1 here, for example, the boiling point of 132 degrees Celsius at 748 torr, if we went ahead and looked, the boiling point of water is 100 degrees Celsius only when the external pressure is 760 torr or 1 atmosphere. So we would see that here it is important to understand that the water is only 100 degrees Celsius as its boiling point at 760 torr, exactly 1 atmosphere. So as you go up into higher elevations with reduced pressure, then the boiling point of water reduces down, and that's the same concept. And so going forward, we can go here, and then this explains kind of what we were talking about before, that the normal boiling point of a liquid is measured at 760 torr, and the dash lines in figure 4.1 to be 60 degrees Celsius of this given liquid. However, you reduce the pressure down to 500 torr, and then you have about 50 degrees Celsius, just as we had discussed prior when we were analyzing the chart here to understand what we were talking about. 60 degrees Celsius here, reduced down to 500. Now we're down to only 50 degrees Celsius needed in order to boil that given liquid sample. So if you suppose that a liquid has a normal boiling point such that it decomposes appreciably when heated to this temperature, this would be some way that we could utilize pressure, because if we reduce the total pressure in the system, we can reduce the boiling point of the sample and no longer decompose this. So sometimes we may have a sample that'll decompose. Let's just say that this liquid decomposes at 60 degrees Celsius, but we need to boil it off to remove it from a system. So what we can do is use vacuum distillation and reduce the pressure of the system, reduce it down to 50, or maybe even safer, reduce it down to be able to boil it at 40. We can safely boil it off. It will not decompose the given sample, and then we'll end up with good product. And then that way we can make sure that no decomposition occurred, and we still have good sample coming out of the entire vacuum distillation system. So going forward into the main topic that we are discussing today is simple distillation, and it allows separation of distillates from less volatile substances that remain as a pot residue at the completion of distillation. So within this, we're only talking about single component distillation. And this is critical here in this next part that I've highlighted, that the difference in the boiling points of each pure substance should be greater than 40 to 50 degrees Celsius. Otherwise, we'd be having to utilize fractional distillation discussed in the other video that I had posted on YouTube. If you need any more review of it, please go back and review that or look at the module from last week. And there is a couple more videos there that you can watch to refresh your memory of that. So for instance, of a system where we would talk about simple distillation, if you have two chemicals mixed together, in this one, diethyl ether as the first one with a boiling point of only 35 degrees Celsius, and then toluene over here at 111 degrees Celsius. So you can see this is a very vast amount of distance in between the two of boiling point. And this would be great to go ahead and toss into your round bottom flask, and then you can set up your simple distillation, and it would easily separate so long as you use very slow heating up to your 35 degrees Celsius for diethyl ether to go over, and then toluene will just stay in your pot residue is what they call it here up at the top. So moving forward, we can see here that they've created a graph here for two different systems, and curve one responds to the dependence of temperature upon the vapor pressure of pure water and intersects at the 760 torr line at 100 degrees Celsius. As we know, water boils at 760 torr. Remember, 760 torr is 1 atmosphere at 100 degrees Celsius. And in this curve 2 is for a solution having a particular concentration of sugar and water mixed together in one system. So we can see that the presence of the non-volatile impurity reduces the vapor pressure at any temperature by a constant amount. And so we can see here that instead, curve 2, instead of boiling over here at 100 degrees Celsius, it would be over here at 105, 110. You have your sugar in here, which is non-volatile, meaning that it does not have the capacity to boil over, to be distilled off of your given solution. And so it actually increases the overall needed amount of temperature, your boiling point has increased here, and it will require more kinetic energy for it to be able to boil over than if you just had pure water. And we're assuming the same vapor pressure here since we're just performing simple distillation. So going forward, looking here, despite the presence of sugar in the solution, the head temperature in the distillation will be the same as for pure water, namely 100 degrees Celsius. So when they talk about here the head temperature, whenever I talked about that still head at the top where the thermometer is in the simple distillation device, the head temperature is the temperature that that thermometer is located at. And it is the temperature of the boiled pure water in the gas phase at 100 degrees Celsius that has come up, and then it's reached that thermometer, and it's there at 100 degrees Celsius, and then it will come off and cool down the condenser back into the liquid phase and then come down into your receiving flask. So we need to make sure that we understand that the head temperature is only 100 degrees Celsius, as it is pure water being boiled off, and the sugar is being kept down in your round bottom flask. As the water distills, the pot temperature will progressively rise because the concentration of sugar in the still pot increases, further lowering the vapor pressure of the water. So the sugar is increasing and then the water is decreasing. So since the concentration of the sugar is increasing, the boiling point required in the pot that holds this combination is going to increase and require more heat to get out more of your pure water from this system. However, the head temperature still remains constant because pure water is the substance that is being distilled off here. So the quantitative relationship between vapor pressure and composition of homogeneous liquid is known as Raoult's law. Equation 4.2, as we discussed at the start, you need to remember that it is the partial pressure of component X equals to the vapor pressure P naught X of pure X, like pure water, like we talked about a moment ago, at a given temperature times the mole fraction N of X of this X water in this example in the mixture. The mole fraction of X is defined as the fraction of all molecules present in the liquid mixture that are molecules of X. So if you have molecules X, Y, and Z within your whole entire system, then the mole fraction of X is just this here, equation 4.3, the mole fraction of X divided by X, Y, and Z added all together. It's similar as to utilizing something like a percent yield or percent composition. You need to understand that the mole fraction of X is equivalent to the moles of X over the total moles of the entire system. And so fortunately, many organic solutions approximate the behavior of ideal solutions. And that is the main idea that we have whenever we're utilizing these sort of systems. Going further into advanced chemistry, you would understand derivations that would come to head of real solutions instead of ideal solutions. But for this class's sake, we'll be utilizing the idea of ideal solutions and utilizing these kind of rounded, I'll call them, equations. So going forward, now that we understand the mole fraction equation here and Raoult's law, we can go ahead and see that if all components other than X are non-volatile, the total vapor pressure of the mixture, and this is very critical, make sure that you understand this. If all components other than X are non-volatile, such as sugar is non-volatile in that water sugar example, the total vapor pressure of the mixture will be equal to the partial pressure of X only. Since the vapor pressure of the non-volatile compounds may be taken as 0, right? They are non-volatile. So we would understand that they don't need to be taken into understanding with regards to creating this equation because they're irrelevant. They're not going to boil. They have nothing to do with the pressure here. Thus, the distillate from such a mixture will always be pure X. That the idea that they're getting here, they're trying to hit home, is kind of a foreshadow towards fractional distillation, because that is a point where you do need to worry about multiple pressures within the system rather than a system where you have water and sugar. You have a volatile liquid and a non-volatile compound within your solution there. Thus, the distillate, so we already discussed that. Going forward, for whenever a mixture contains 2 or more volatile compounds, however, the total vapor pressure is equal to the sum of the partial pressures of each component, known as Dalton's law. So we've already discussed at the start here, but I'll go ahead and review this since we have our equation in front of us. The pressure of the total system is equal to component X, Y, and Z. If you had 3 components in this given system, it'd be the pressure of X plus the pressure of Y plus the pressure of Z, and that creates your whole total system that you can add all together. So make sure to list these equations within your lab notebook. They may not be utilized within your post-lab questions much other than right here I can see this is more of an explanation, but I would go ahead and have those in your lab notebook so that way that you have a demonstration of understanding why these concepts are important in the grand schema of distillation. So going forward, make sure that you follow through the procedure and write down any sort of safety hazards we may have here. Coming back, we'll review this simple distillation apparatus setup one more time. Please make sure when you write your notebook, and I'm just going to hit this point home again because I noticed it on almost everybody's notebooks from the start, your apparatus is more than just simple distillation apparatus setup. Please don't write that. If you want to write down your simple distillation apparatus setup, then list out everything here, and then you'll get full credit. That is all that I want to see in your lab notebooks. Right here, you can see we have support stands to hold together our simple distillation apparatus. But what is the simple distillation apparatus? I'm going to hit this point home so that everyone really understands. So that way, if you were to go into a lab, you could be able to perform a simple distillation. It is the support stands holding up your support ring, which holds an electric flask heater or a heating mantle or a hot plate, such that we won't use a Bunsen burner within this given experiment because you will be utilizing a volatile compound that is flammable, cyclohexane. So we would never use a Bunsen burner because you could potentially ignite your cyclohexane or cause an explosion, which we would never want to have. So we will stick to our electric equipment. You'll have 2 boiling chips in here or a stir bar in order to allow boiling and surface area to coincide and have your heat completely homogeneous throughout your mixture. This will be your pot, or a round bottom flask is what we call in the lab. Here is your distilling head, or your adapter, as they call, but we define this as our distilling head because that is the head of the distillation device. The simple distillation apparatus is the head where your sample goes from the liquid phase up into the gas phase and then meets at the distillation head, the still head, as well as what they call it. And their thermometer, you want to make sure that it is up here near the still head, because you want to make sure that you are measuring the temperature not of the boiling substance in your still pot, but the temperature of your pure substance that has risen up into the gas phase. Here, the thermometer adapter allows the thermometer to be stuck in. It's just a rubber piece that goes at the top of your adapter here. Then here is your condenser coming here, allowing water in, as you can see from the bottom, going through, cooling down your condensate, and then your rubber tubing coming out, pulling the hot water out of the system. Your clamp holds your condenser to the support stand as well. You can see there's a little clamp here holding your round bottom flask. And finally, the adapter that allows your liquid to come out after it has distilled off down into your receiver. That can be a flask or a graduated cylinder. And so going forward, make sure to go ahead and review everything here and utilize this within your lab notebook. And let me go ahead and stop the share here, so that way I can review to see if I have any other critical info. Make sure whenever you would be performing this to utilize grease on the little joints, so that way none of the glassware gets stuck and then you can't remove it after you perform your experiment. Additionally, whenever you clean, we always want to use firstly soap and water, secondly DI water to remove any sort of additional deposits that may be within the tap water in our sinks at the lab. Then you will also use acetone, which is a good polar protic solvent that not only can actually dissolve non-polar compounds, it can also dissolve polar. So it will dissolve water off of your glassware, and will also dissolve anything like cyclohexane or any other sort of solutions that you would have within your glassware. And finally, we can also utilize hexane to remove the grease off of the joints after we're done, just to keep it clean, because grease can get a little oily and get stuck on any of our substances afterwards. So that looks like about all that I have here for today. So I'm going to go ahead and stop our recording and open up the floor for anyone to ask questions.